Alright, buckle up, because the air war you think you know, it's gone in less than 2024 days. Seriously, by the time we hit 2030, the pilot might not even be human. The wingman flying alongside them might not have a cockpit at all, and that terrifying missile you're bracing for won't just scream in at Mach 3. Oh no, it'll glide silently at Mach 7, completely invisible to radar. Are you ready to meet the jets that are about to make even the mighty F-22 look like a clunky old flip phone? Because what's coming next is going to redefine everything we understand about aerial warfare. Why the 5th gen era is already on life support. Let's be honest, the F-22 Raptor is still an absolute beast, a marvel of engineering that, when it first flew, felt like something out of science fiction. It's the undisputed king of dogfight stats, a true air superiority fighter. But here's the kicker. There are only about 187 combat-coded airframes in existence, and every single one of them is, quite frankly, older than TikTok. Think about that for a second. Its design roots stretch back to the late 1980s, and while it received upgrades, the core architecture is showing its age in a world moving at warp speed. Then you've got the F-35, a phenomenal multi-role fighter that can see farther than almost anything else out there, fusing an incredible amount of information for its pilot. But guess what? Its initial design was conceived when the very first iPhone was still rocking a home button. Technology moves fast, doesn't it? What was cutting edge even a decade ago is now contending with completely different threats. Meanwhile, our adversaries haven't been sitting still. China's J-20, for example, isn't just a stealth fighter. It's now flying with new, low-observable engines that further enhance its capabilities, pushing the envelope in terms of stealth and performance. Russia's Su-57, despite its troubled development and limited production numbers, is actively sparring over Ukraine, gaining real-world combat experience and refining its tactics against modern air defenses. Both of these nations are also pumping out incredibly advanced long-range surface-to-air missiles, SAMs. Faster than Western powers are producing new Raptors. These SAMs are designed to deny access to airspace, making even stealth aircraft vulnerable if they get too close. The math, when you look at it, is brutally simple and profoundly concerning. Limited numbers of aging, albeit capable airframes, paired with computer cores that are struggling to keep up with the processing demands of tomorrow's battles. Add to that shrinking basing options, as long-range precision strikes and anti-access area denial, A2AD strategies make forward airfields increasingly vulnerable. If you want to survive, let alone dominate, the skies of the 2030s, you don't just need an upgrade to your current jets, you need a completely new playbook. You need a paradigm shift. Enter the 6th gen family of systems. So, what does this new playbook look like? Forget thinking of a 6th generation fighter as just another sleeker airplane. That's missing the forest for the trees. Instead, picture it as a meticulously choreographed three-piece orchestra, where every instrument plays a vital interconnected role. This isn't about a single hero aircraft. It's about a symbiotic network of machines and humans working in concert. First chair, you've got the mothership. We're calling it NGID, or maybe the F-47, or across the pond it's the Tempest. Whatever the name, this is your stealthy, long-range, optionally manned centerpiece. What does optionally manned mean? It means this incredible machine can fly with a human pilot at the controls for complex decision-making. Or it can operate fully autonomously on missions deemed too risky or too mundane for a human. It's built for deep penetration, for pushing the envelope in contested airspace, and for acting as the central nervous system for the entire aerial formation. It's not just a fighter. It's a command and control node, a sensor fusion hub, and a potent weapon platform all rolled into one. Second chair brings in a swarm of AI-flown loyal wingmen. Officially, these are the Collaborative Combat Aircraft, or CCAs. Think of them as unmanned combat aerial vehicles, UCAVs, that fly alongside crewed aircraft. But with a crucial difference. They're not just drones. They're truly autonomous, making self-contained combat decisions within human-defined parameters. The vision? These CCAs are priced like a pickup truck, relatively speaking, of course, and flown with the agility and responsiveness of a gamer's reflexes. They're meant to be numerous, affordable, and critically, expendable in ways a human crewed fighter simply isn't. They can perform a range of missions, from air-to-air and air-to-ground combat to electronic warfare, and even acting as decoys or missile sponges. And then, The third chair, everything else in the cloud. This isn't just about the aircraft themselves. We're talking about a vast, interconnected ecosystem that includes satellites providing global communication and surveillance, tankers extending reach, naval ships offering long-range detection and missile defense, and ground troops feeding real-time intelligence. All of these disparate elements are woven together, sharing one massive living data picture. This isn't just about passing data. It's about fusing it, analyzing it with AI, and presenting it in a way that gives every participant, from the pilot in the mothership to the ground commander, an unprecedented level of situational awareness. Alone, each piece of this orchestra is useful, even impressive. But together they don't just upgrade air warfare. They completely rewrite its physics, creating a force multiplier that's exponentially greater than the sum of its parts. AI that flies, fights, and forgets to blink. Let's talk about the brain of this new air combat ecosystem. Artificial intelligence. Today's F-35 is already a marvel, capable of fusing 8 distinct sensor streams into a coherent tactical picture for the pilot. It's an incredible feat that dramatically improves situational awareness. But tomorrow's AI, that's going to fuse not 8 but 800 sensor streams. Imagine the sheer volume of data. Optical, infrared, radar, electronic intelligence, signals intelligence, cyber inputs, all flowing in simultaneously, processed and correlated in milliseconds. It's like going from a single telescope to a global observatory, all condensed into the cockpit. These aren't just fancy algorithms. These are sophisticated AI models trained on millions, if not billions, of simulated dogfights, complex tactical scenarios, and real-world data. They can now pick the optimal intercept course, identify the weakest link in an enemy formation, or even predict an adversary's next move in a mind-boggling 0.03 seconds. Think about that. A task that takes a human backseater, an elite, highly trained individual, a good 3 seconds to accomplish on a good day, the AI does almost instantaneously. This speed isn't just an advantage. It's a revolutionary leap that can mean the difference between victory and defeat. And here's the kicker, the part that truly changes the game. The AI isn't just advising the human pilot anymore. It's cleared to pull the trigger. Now, before you start envisioning Skynet scenarios, let's clarify. Crewed pilots absolutely remain the flight commander. They set the mission intent, define the rules of engagement, and establish the ethical boundaries. They are the quarterback calling the plays. But within those parameters, they can delegate risky entries, complex maneuvers, or even lethal actions to the machine. The AI can process threats, consider tactical options, and act, all in milliseconds, far faster than a human pilot. For example, a CCA could detect an incoming surface-to-air missile, take evasive action, deploy countermeasures, and resume formation, all without needing direct input. Think of it this way. It's like having a wingman who's not only memorized every single after-action report since 1950, every tactical manual and every enemy doctrine, but also has the processing power to apply all that knowledge instantly. And this wingman? It never needs oxygen, never gets tired, and never has a moment of doubt. This dramatically reduces pilot workload in high-stress situations, allowing the human to focus on the broader strategic picture, while the AI handles the lightning-fast tactical execution. It's about leveraging the best of both worlds, human intuition and strategic oversight combined with machine speed and precision. Stealth after stealth. For decades, stealth has been the holy grail of air combat. Fifth-generation jets like the F-22 and F-35 were designed to hide from radars that were, largely, sculpted in the 1990s. They achieved this with revolutionary low-observable shapes and radar-absorbent materials. But radar technology, like everything else, hasn't stood still. The threat landscape is evolving rapidly. Sixth-generation fighters aren't just aiming to evade today's radars. They're designed to beat the radars of the 2040s. We're talking about incredibly sensitive gallium nitride, GaN, ASA, active electronically scanned arrays. These GaN radars are so powerful, so precise, and so capable of operating across a wider spectrum of frequencies that they could theoretically spot something as minute as a seagull's heartbeat at significant range. They offer enhanced power, sensitivity, and bandwidth compared to older radar technologies. So how do you disappear from something that sensitive? The answer is threefold, pushing the boundaries of physics and material science. First, you've got tailless flying wing shapes. This isn't just about looking cool, it's about fundamentally changing how radar waves interact with the aircraft. Traditional aircraft, even stealthy ones, have vertical and horizontal stabilizers, tails and wings, which create distinct 90-degree corner reflectors that, no matter how subtly, can reflect radar energy back to the source. By eliminating these, you remove those critical radar hotspots, drastically reducing the aircraft's observable signature. It's about designing an aircraft that doesn't just absorb radar, but fundamentally doesn't present a reflective surface in the first place. Second, embedded antennas. Think about every antenna, every sensor aperture, every gap or seam on a traditional aircraft. Each of those is a potential radar reflector or a vulnerability in the stealth design. 6th-gen jets are moving towards embedded antennas that literally double as structural elements of the airframe, cutting those radar-reflecting apertures to near zero. It's a seamless integration, where the aircraft skin itself becomes the sensor and communication array, presenting an incredibly smooth, uninterrupted surface to radar waves. Third, and perhaps most mind-bending, adaptive skin coatings. Imagine a chameleon, but instead of blending into its visual surroundings, it's actively adapting its electromagnetic properties to defeat radar. These aren't just passive radar-absorbent paints. These are advanced, potentially metamaterial-based coatings that can dynamically shift their reflectivity in real time, perhaps even changing their electrical properties to actively cancel out incoming radar waves. It's about being a ghost in the electromagnetic spectrum. The net result of these combined innovations? An all-aspect signature, meaning from any angle, that's lower than a golf ball and, in terms of its radar cross-section, the size of a commercial refrigerator. That's not just stealth. That's electromagnetic invisibility. Hypersonic weapons that launch inside the fence. When you hear hypersonic, your mind probably jumps to those dramatic Hollywood boosters climbing 100 miles into the exosphere before diving back down. And while those are certainly real, the 6th-gen approach to hypersonic weapons is far more insidious, designed for tactical advantage, not just strategic deterrence. Forget the massive externally carried weapons that betray a jet's presence. 6th-gen internal weapons bays are sized for compact hypersonic cruise missiles. We're talking about weapons that are small enough to be carried internally, preserving the aircraft's precious stealth. These aren't just rockets. They're often two-stage solid ramjet combos. What does that mean? It means they get an initial boost to high speed, and then a ramjet engine kicks in, allowing them to sprint at sustained speeds of Mach 7 or even higher. And the truly revolutionary part? They fit where an AMRAAM, a standard air-to-air missile, used to ride. This miniaturization of hypersonic technology is a monumental engineering achievement, allowing stealth fighters to carry multiple such weapons. But what powers the jet itself to get these weapons into position? That's where adaptive cycle engines come in. These are game changers. Unlike traditional jet engines that are optimized for either high-speed combat or fuel-efficient cruising, an adaptive cycle engine can dynamically adjust its airflow. It can flip from a high bypass mode, perfect for fuel-efficient loitering over vast distances, to a high combat power mode, delivering incredible thrust without needing to kick in the noisy, heat-generating afterburner. This flexibility translates directly into a combat radius north of 1,000 nautical miles on internal fuel alone. That's a massive leap in unrefueled range. What does this mean in real-world terms? Translation: the jet can take off from a remote base like Guam, strike deep into contested territory like Taipei on day one of a conflict, deliver its hypersonic payload, and still have enough gas in the tank to tango with any interceptors on the way home, or even hold station for further tasking. This kind of unrefueled range fundamentally changes strategic calculus, reducing reliance on vulnerable forward bases and making the aircraft a truly global power projection tool. It's about delivering devastating kinetic effects from unexpected vectors, deep inside enemy territory, before they even know what hit them. The wingman that cost less than a Tesla. Let's talk numbers, because this is where the 6th-gen family of systems truly shines in terms of practicality and strategic mass. The U.S. Air Force isn't just dabbling with loyal wingmen. They want 1,000 collaborative combat aircraft, CCAs. The Navy isn't far behind, aiming for 400 of their own. That's a serious commitment to unmanned systems. And the target unit flyaway price? A cool $18 million. Now I know what you're thinking. $18 million is a lot of money. And yes, it is. But consider this. A single F-35 can cost upwards of $110 million, and a crewed 6th-gen fighter is projected to be around $300 million or more. So in the grand scheme of advanced military aviation, $18 million for a sophisticated jet-powered drone is, comparatively speaking, a steal. It's priced like a very high-end pickup truck when compared to a supercar. For that sticker price, you're not getting a toy. You're getting a roughly 30-foot drone, a substantial aircraft, that's capable of a staggering array of missions. It can engage in air-to-air combat, conduct precision air-to-ground strikes, unleash electronic jamming to disrupt enemy communications and sensors, or, perhaps most critically, act as a missile sponge. What does missile sponge mean? It means it can deliberately draw enemy fire, forcing adversaries to expend their valuable, limited, and expensive missiles on a relatively cheap unmanned asset, thereby protecting the much more valuable crewed mothership. Crucially, each CCA plugs into the exact same software architecture as its mothership. This isn't just about communication, it's about seamless interoperability. This common digital backbone means that tactics can scale exponentially, like adding another player to your online gaming squad, instantly integrating them into the team's strategy. If you lose one of these CCAs over contested seas, perhaps to an enemy air defense system, it's a serious incident, yes. It's a congressional phone call, requiring explanation and potentially budget adjustments. But it's absolutely not a national funeral. Not the devastating loss of a highly trained human life and a multi-hundred-million-dollar crewed asset. This changes the risk calculus entirely, allowing for more aggressive tactics and operations in highly dangerous environments. Program Showdown. Who is building what? The race for 6th-generation air dominance is a global one, with major powers and alliances pouring immense resources into these next-gen platforms. It's not just about building a better plane, it's about securing future air superiority. In the United States, the focus is on next-generation air dominance, or NGAD. This isn't just a single aircraft program, but a family of systems, and we already know that 2 competing stealth prototypes secretly flew back in 2020. While details are still highly classified, the smart money is on the winner, likely an aircraft designated the F-47, possibly from Boeing, to enter service around 2030. The Navy has its own parallel program, known as Navy NGAD or the FA-XX, which is expected to follow 2 years later, replacing their aging FA-18EF Super Hornets and complementing the F-35C. Budget documents hint at a future force structure of around 200 crewed fighters backed by a staggering 1,000 CCAs, illustrating the human-machine teaming approach. Across the Atlantic and into the Pacific, the UK, Italy, and Japan have joined forces for the Global Combat Air Program, or GCAP. This ambitious trilateral venture brings together industrial heavyweights like Rolls-Royce, BAE Systems, Leonardo S.p.A., and Mitsubishi Heavy Industries. Their vision includes merging advanced sensors into a single massive eye-stare antenna, rumored to be the size of a dinner table, offering unprecedented situational awareness. The first flight of a demonstrator is slated for 2027, with the full system entering service around 2035. This collaboration aims to share costs and leverage diverse expertise, creating a formidable force. Not to be outdone, France, Germany, and Spain are collaborating on their own Future Combat Air System, or FCAS, while industrial giants Airbus and Dassault have reportedly had their share of arguments over intellectual property and work share. A common challenge in multinational defense projects. They did manage to fly a demonstrator in 2023. Their promise is a comprehensive 6th-gen jet paired with a swarm of remote carriers. These aren't just loyal wingmen. Think of them as specialized drones designed to perform specific high-risk tasks, perhaps even kamikaze enemy radars to clear a path for the manned fighter. Then there's China. While official details are scarce, whispers and leaked images on social media from December 2021 hint at advanced projects like the J-36 and J-50. Rumors describe tailless delta wing designs, possibly with 3 engines, and the ability to supercruise at Mach 2+. Beijing hasn't confirmed anything, of course, but satellite pictures don't lie. A test runway in Chengdu has been conspicuously busy with new, unfamiliar aircraft since 2022, suggesting significant progress. China's rapid advancements mean they are a serious contender in this race. Finally, Russia. Their single-engine checkmate teaser from Max 2021, while visually striking, is largely considered a fifth-gen light aircraft, struggling with development and production. The real sixth-gen effort remains shrouded in black project secrecy. Insiders whisper about a MiG-41 interceptor, a concept that borders on a spaceplane designed for extreme altitude and speed. However, given Russia's current economic realities and industrial limitations, a realistic service entry date for a true sixth-gen fighter looks like 2035 at the absolute earliest, if ever. The global landscape is intensely competitive, and each nation or alliance is carving out its own path to the future of air power. What networked war looks like from the cockpit. Okay, let's paint a picture. Imagine yourself strapped into the cockpit of an F-47, the ultimate sixth-gen mothership. You're punching through contested airspace at a dizzying 60,000 feet. The curvature of the Earth visible from your canopy. Ahead, your sensors detect a pair of enemy J-20s patrolling, their own stealth signatures faint but present. Instead of charging head-on, which would be a fifth-gen move, you ghost the net. What does that mean? You reduce your own electromagnetic emissions to near zero, going dark, becoming a true phantom in the sky. Then, with a subtle command, you release 3 collaborative combat aircraft, CCAs. These aren't just drones, they're your loyal AI-driven wingmen. They sprint low, hugging the terrain, deliberately activating their electronic warfare suites to draw enemy radar cones. The J-20s, now alerted to something, but unsure what, are forced to react, revealing their positions and emitting more signals. Suddenly, a critical piece of intelligence flashes across your multifunctional display. A Navy destroyer, far off the coast, has tipped off an impending Su-35 launch from an airfield 400 miles to the west. This isn't just radio chatter. It's seamlessly integrated data, instantly correlated and presented by your AI. Your AI, without even needing a verbal command, tasks one of your loyal wingmen. This drone, acting autonomously but within your predefined parameters, climbs rapidly to 80,000 feet, a suborbital trajectory. At the apex of its arc, it releases a compact hypersonic strike weapon. The weapon, now on its own, boomerangs down, traveling at Mach 7, targeting the Su-35's runway. The precision is staggering. The weapon impacts the runway, creating a massive crater, just moments before the Su-35's wheels would have left the tarmac. The launch is aborted, the threat neutralized before it even becomes airborne. By the time the J-20 pilots realize they've been hunting ghosts, their radars confused by the CCAs, their airfield under attack from an unseen force, your mothership is already tanking over friendly skies, quietly replenishing its fuel. You check your mission display. The scoreboard reads 4-0. No human lives risked, multiple threats neutralized, and you, the pilot, were the orchestrator, not the primary target. That's what networked war looks like from the cockpit of the future. Mid-roll CTA. If this deep dive into the future of air combat is bending your mental G limits, don't eject just yet. Hit that subscribe button and ring the bell so you don't miss our next ride. Because next time, we're going to be looking at the cutting-edge laser defenses that could swat these hypersonics right out of the sky. You won't want to miss it. Challenges. No one put on the poster as revolutionary as sixth-generation fighters sound. It's not all smooth sailing and sci-fi dreams. There are monumental challenges lurking behind the glossy concept art, issues that no one puts on the marketing posters. First up, cybersecurity. Every single new data pipe, every sensor stream, every networked connection that makes this family of systems so powerful is also a potential hackable door. These aircraft are essentially flying supercomputers, and that makes them incredibly vulnerable. Imagine an adversary gaining control of a loyal wingman, feeding false data to the pilot, or even disabling critical systems mid-flight. The implications are terrifying. Protecting these complex interconnected systems from sophisticated state-sponsored cyber attacks is arguably as crucial as their stealth or speed. It's a constant evolving battle against unseen threats that could compromise operational capabilities and jeopardize mission success. Then there's the issue of heat. Those compact hypersonic weapons we talked about, they generate an insane amount of heat. The internal bays that house them can bake at temperatures exceeding 1800 and the weapons themselves can reach upwards of 2500 degrees C. Traditional aerospace materials simply melt or degrade under such conditions. So, engineers are pushed to the absolute limits of material science, growing exotic single crystal metals with microscopic cooling vanes, developing advanced ceramic matrix composites, and pioneering adaptive thermal protection systems. It's an almost unimaginable engineering feat to design components that can withstand such extreme thermal loads while remaining lightweight and structurally sound. Next, the elephant in the room, ethics. Specifically, will Congress or any governing body for that matter rubber stamp an AI kill decision? This isn't a hypothetical. The technology is advancing to a point where AI can identify, target, and engage without direct human input in real time. While the current doctrine emphasizes human in the loop or human on the loop, defining those boundaries and ensuring accountability is a profound moral and legal dilemma. Can a machine truly understand the nuances of proportionality and discrimination in warfare? What happens when an AI makes a mistake? Who is ultimately responsible? These are questions that demand answers before widespread deployment, and of course, computer money. All this cutting-edge technology comes with an astronomical price tag. The U.S. Air Force alone needs an estimated $120 billion through 2040 for the NGAD program. That's the same decade that critical social programs like Social Security are projected to start wobbling under immense financial strain. Can a nation afford to invest so heavily in such advanced, expensive systems while facing other pressing domestic needs? The cost-effectiveness of these programs, especially the crewed element, which could be $300 million per aircraft, is a constant point of debate and a significant hurdle for their long-term viability. Finally, and perhaps most subtly on pilot trust, surveys still show that a significant portion of aircrew, as high as 63%, still want their fingers on the trigger. There's a deeply ingrained human element to combat, a reliance on instinct, experience, and the moral weight of decision-making. How do you build trust between a human pilot and an AI wingman that's making autonomous, lethal decisions? How do you overcome the natural human skepticism and fear of relying on a machine for your life? As the saying goes, culture beats circuitry every time. Until pilots fully trust these autonomous systems, their full potential might remain untapped. Cascading effect on every other airframe. The arrival of sixth-generation air combat systems won't just be a new chapter, it'll be a complete rewrite for the entire Air Force. Once NGAD, GSAP, and FCAS truly come online, the ripple effect will be felt across every existing airframe, fundamentally reshaping their roles. The venerable F-22 Raptor, for example, the king of air superiority for decades, will likely head to the boneyard. Its limited numbers and aging systems, despite its legendary capabilities, won't be able to compete with the holistic, networked power of the new generation. It's the end of an era, but a necessary one. The F-35, a marvel of sensor fusion and stealth, will likely morph into a specialized bomb truck. While its stealth still makes it invaluable for penetrating contested airspace, its primary role might shift to carrying larger internal payloads of standoff weapons, clearing the way for the sixth-gen fighters. It becomes a critical component of the strike package, but no longer the spearhead of air dominance. The F-15EX Eagle II, the latest variant of the F-15, will find its niche as the homeland defender and potentially a missile truck. With its immense payload capacity and advanced sensors, it's perfectly suited for protecting national airspace, launching long-range weapons from safe distances and even controlling CCAs, without needing the deep penetration stealth of the F-35 or NGAD. And yes, the beloved A-10 Warthog, a close air support icon, will finally truly retire. Its mission, while vital, will likely be taken over by more survivable and versatile platforms, including armed drones. For allies across the globe, the arrival of sixth-gen fighters presents a stark fork in the road. They'll face a critical choice. Either buy into the immensely expensive and complex GCAP or FCAS programs, committing to the cutting edge of air power, or accept a second-tier status with upgraded fourth-generation aircraft. This decision isn't just about hardware. It's about strategic alignment, industrial partnerships, and maintaining relevance in future conflicts. Those who don't adapt risk being left behind. Meanwhile, the global arms race is already reacting. China's carrier fleet is actively training against sophisticated drone swarms in the South China Sea, perfecting tactics for both offensive and defensive unmanned operations. This clear demonstration of emerging capabilities means that every regional power, from Australia to India, is now scrambling to acquire loyal wingmen of their own, or develop similar indigenous capabilities. The arms race isn't just climbing steadily anymore. It's pole vaulting into an entirely new dimension, driven by the disruptive potential of AI and autonomous systems. Conclusion: the question we'll answer together. So by 2035, the sky will undoubtedly hold fewer human pilots and significantly more silicon. Sixth-generation fighters won't just be incrementally faster or stealthier than their predecessors. They'll represent the first true combat aircraft designed from the motherboard up to fight as a seamlessly integrated team. One human orchestrator, commanding many intelligent machines. This future, where AI-driven wingmen and hypersonic weapons are the norm, might feel thrilling to some, a testament to human ingenuity and technological progress. To others, the idea of autonomous warfare and machines making lethal decisions might be terrifying, raising profound ethical and existential questions. Ultimately, whether it excites or unnerves you might just depend on which side of the radar you happen to sit. So I have to ask you, would you trust an AI wingman with your life? Would you fly into combat knowing a machine, albeit a brilliant one, has the final say on certain actions? Drop your take in the comments below. Let's fly into that future together, because the next war may very well be won by the side that codes fastest, not just shoots straight.